Hello, everyone. Good evening. This is a late evening talk, so really appreciate everybody showing up. I'm guessing some of the parties have already started, so hopefully this one will be worth it. So I'm Vivek Ramachandran, and I'll be talking about breaking secure web gateways for fun and profit. Quick introduction. Did my very first DEF CON talk way back in 2007, 17 years back. Been working in cybersecurity for the last 25 years, found multiple attacks. I was the creator of the Cafe Latte attack and a couple of others. Then founded Pen Tester Academy, and now I run a browser security company called SquareX. Now, this has been a very big team effort. Some of the great folks are here. I'll just allow them to introduce themselves.
Hello, everyone. I'm Shaurya, happy to be here. I work as the principal software engineer at SquareX, and my research interest is mainly around browser extensions. Happy to be here.
Good evening, everybody. My name is Dakshita. I do security research at SquareX, and happy to see so many faces in the crowd.
Jeswin couldn't be here, last-minute US immigration problems, but he sends his regards. Hopefully the audio will play. If not, we also have captions. Okay, looks like I have the one without the captions. So he's basically saying, hey, I wish I could be here. Thank you so much for attending the talk. Hopefully you love it. And if so, give me a shout out. I just made that up. But hey, amazing guy. Wish he could be here. But it is what it is. OK. So, the browser has now become the computer, right? You literally have most folks do 90% of all their work on the browser, right from accessing cloud storage to documents to transactions and whatnot. Now, in the enterprise, if you look at secure web browsing, you have this cloud component called secure web gateways, which are part of SASE SSE solutions. Maybe that's one of the vendors trying to put a stop to this talk. And then you also have endpoint security. And endpoint security, as we all know, has zero visibility into the browser. Now, when it comes to secure web gateways for this talk, I'm actually going to treat it as something which can do SSL interception, malware detection, DLP, sandboxing, and a bunch of stuff. Now, different vendors like to slice and dice this in different ways, but we've kind of put all of that together. So this makes it a much more rigorous exercise when we try to look at secure web gateways. Now, SASE SSE, which is kind of the overarching business aspect of secure web gateways, CASB, and a bunch of other stuff, is a massive market. That's the Gartner Quadrant completely blanked out. The idea wasn't to vendor bash, but every single vendor in the SASE, SSE, and secure web gateway, Gartner Quadrant and beyond, is vulnerable to the architecture attacks that we are about to discuss. This is a ginormous market. What does the B in there stand for? Bugs. So 80 billion, but also a bunch of bugs in there. Now, the mandatory requirement, if you're a SASE SSE vendor for secure web gateways, is the first one, which is you need to be able to stop malware from downloading, threat prevention, and URL filtering. And what this talk is primarily going to show is, unfortunately, secure web gateways are unable to do this, and it is actually an architectural problem. And this is not a software bug. So one of the other things, interestingly, is the service level agreement. SLAs are interesting because this is what vendors promise their customers. Now, I've completely paraphrased this based upon a bunch of SLAs, so you don't go back and Google this and figure out which vendor. But literally what everybody states is we guarantee that we can prevent 100% of all known malware and viruses contained inside websites from leaking through our web proxies. And they are supposed to give you service credits for every single leak that happens. So I'm guessing it's going to be a large number of service credits next calendar month. Okay, this is a lot more comfortable. So I'm going to crank my neck. So what are the challenges for secure web gateways when it comes to attack detection? Now, unfortunately, if some of you might be old enough to remember, secure web gateways and SSL-intercepting proxies came to be almost 15 to 20 years back. Interestingly, SSL was becoming popular, unbelievable. Back in those days, most of it was HTTP. And at that point in time, enterprises needed a way by which they could monitor traffic, block things. The web was much more simpler. Web applications were much more simpler. Now, unfortunately, what SWGs are trying to do is look at network traffic and infer application layer attacks. Now, which basically means they have absolutely no web app context, no user awareness context, no concept of windows and tabs. And without all of this information, they need to go back and infer and figure out what attack is really happening on the browser side. There's also cloud processing limitations. Now, this isn't based upon any tests that we did. This is based upon public documentation available on SASE, SSE, SWG vendor websites. The numbers in there aren't a typo, if you're wondering. Some vendors cannot go ahead and scan file sizes more than just 15 MB, and most of them in the 50 MB range. Now, what this means is if you're applying an enterprise policy, beyond these file sizes, you need to do a blanket allow or a blanket block. Those are the only two choices that you have. Now, regarding file type scanning, there's a fair amount of aberration between the vendors. Zip files and archives, especially multiple recursion levels, notoriously bad when it comes to scanning. Now, why, right? Everybody's wondering, hey, why do vendors have to live with these limitations? I mean, ideally, you could probably throw a lot of CPU and memory and scan entire files. So this looks very unusual. Till the time you kind of go back and remind yourself the way these products are priced. So with the traditional 80% discounting, which every vendor does, I mean, people in procurement know that all too well, SASE, SSE vendors typically go ahead and sell at somewhere between $2 to $4 per endpoint or per user per month. Now imagine for a SASE gateway to look at millions of files per second and spending a massive amount of compute and CPU power and memory, right? It's going to be cost prohibitive. So how does file scanning really work in secure web gateways? Now, anytime a user ends up clicking a link to download a file, a secure web gateway is the one who receives all the traffic from the user's browser. It ends up seeing a content disposition header trigger, couple of other ways as well. And it says, you know what? There's a file downloading. Let me go ahead, cache this in the cloud, start my scan, and if I find something is suspicious, then I'm going to go block it. Similarly, when it comes to websites, HTML, CSS, JavaScript, imagine that there's a new spear phishing website which was set up using heuristics, AI, ML, whatever you want to throw at it. The vendor ends up detecting it. Ideally, all of them claim that they fingerprint this. So if the attacker were to simply take that website, put it on another URL, they should still be able to block it. Okay. So what is the core difficulty and the big issue with the architecture, right? Now, secure web gateways, unfortunately, are only looking at network traffic. The attacker has a compute machine available after the HTML, CSS, and all the files leave the proxy. And that compute machine is your web browser. Browsers over the last 7 to 10 years have become very, very capable. honestly almost, if not more complex than your operating system. Like Chromium source code, if any of you have taken a look, is close to a couple of million lines. So in the browser, you have a bunch of things happening when a site loads, right? You have DOM changes, you have various browser events, user interactivity, and whatnot. Unfortunately, the SWG does not have access to all of this data. And this is really where it is operating in the blind. It's also impossible to sync all of this live back to the cloud, because imagine every time you click something, that data gets synced back. So what are we going to talk about? So this was really about the basics of SWG and how they work. Today, we are going to look at techniques which allow you to fully bypass malware detection and malicious file detection on secure web gateways. Now, in my mind, 3 different classes. The first is pure client-side attacks, things like clickjacking and whatnot. Those are simple to understand as to why a SWG can't pick it up, because it's extremely client-side. The second is unmonitored channels, and the third is what we've coined as last mile reassembly attacks. And we'll go through the 2 in more detail. Unmonitored channel attacks. Now, this is very interesting, is because there are so many new protocols. Unfortunately, SWG vendors find it extremely difficult to go ahead and keep up and try to build monitoring and interception for all of them. Also, some of these protocols are traditionally difficult to intercept and analyze. But before that, let's actually look at how a SWG typically works. So the first example we're going to look at is file download without a secure web gateway, right? And what we are doing is, right after this talk, we'll make a website online called browser.security. If any of you use SASE, SSE, web proxies, you can go and test it right after this talk. How many of you use SASE, SSE, web proxies? Just 5, 10? Okay. So what we've done is, on the very left-hand side of the screen, these are attacks with SWGs can detect right out of the box, which is a malicious file ends up downloading, a known malicious website is visited, and all of that. So without a secure web gateway, what happens is, if we go ahead, try to download a known malicious file, which is there literally in every thread feed, as expected, this downloads. We'll check this with VirusTotal. We can see it's clearly vulnerable. And now, actually, let's look at the same example with a secure web gateway turned on. How many of you would like to see a vendor logo show up now? No way. You can try this at home. This is one of the experiments you can try at home. OK, so vendor class 1. Now, what these vendors do is, the moment a file download starts, they cache the entire file in the cloud. They run the whole scan. And only once they feel this is benign, they go ahead, allow the download. So in this case, this is known malicious. The moment we click on it, you'll actually see the attack was blocked. We weren't able to download it, right? Now, vendor class 2. Personally, I actually found this very unusual. So probably because all vendors are really going ahead and competing with each other on trying to make things more seamless, vendor class 2 will actually allow the file download to begin. But at any point in the cloud, if they feel they probably saw malware signature, they kill the download in between. So very weirdly, you actually get a truncated file. So this is vendor class 2. You'll now see that we have a 14 KB file rather than the 114 KB which was downloaded previously. The exact same file, but truncated. file upload. Now, why is file upload interesting? Almost every single SASE SSE vendor would basically go ahead and say, we allow you to go ahead and build out web DLP rules, right? So if somebody is uploading a file, there is an insider attack, then you can have all of these regular expressions or something else that you can check in the proxy. And based upon that, you can block the file upload. Now, in this case, we've just used a malicious file upload to show you. It works without the proxy, and the moment you can clearly see right now. Now, with the proxy, this will get blocked. And this could have been a DLP rule, doesn't need to be a malicious file. I think showing with a malicious file is a lot more easier. And you can see now this was blocked. Okay. We'll come to the website at the very end. Okay. Okay, so we now know how SWGs function. Let's actually pick the simplest attack. I almost feel bad for showing this because honestly, I don't even think it's an attack, but hey, works. Unmonitored channels. So communication channels and protocols like WebRTC, WebSockets, Web Transport, gRPC, server-side events, WebTorrent, and even Firebase cloud messaging, this is currently completely unmonitored, is not intercepted, is not looked at by almost all web proxies at this point in time. So what this really means is you could literally smuggle a malicious file, a very, very well-known one in all threat feeds, for what it's worth, even WannaCry, any ransomware, right through a WebRTC channel or right through a server-side event channel. Now, probably a year, 2 years back, it did require a little bit of coding finesse to go ahead and build these out. But now with code LLMs, it's actually fairly easy to go ahead and do this. A lot of the demos which we built and what we are putting out, one of our interns actually built it literally with ChatGPT's help. And this was something we very consciously did just to show that any attacker, if he knows and is aware of this, could actually build it himself. So how does this work? Well, you are on a secure web gateway. Unfortunately, it does not monitor many of these channels. Many SWG vendors try to force enterprises to block these communication channels on the browser. But if you block WebRTC, your entire user experience is going to come down in a very big way, right? I mean, these protocols were built to make real-time communication be a lot better. So let's take a look at how this looks like. Now, we have a ton of demos, and that's why we're kind of going through very quick videos. Later, you can just go to browser.security and just try it out yourself. Okay. So what we've done is, when you go to browser.security after this talk, we have all of these different classes of attacks that we put out. The third column is unmonitored channels. And really, all we are doing is when you click on, let's say, WebRTC, we use WebRTC as the carrier medium for the same malicious file that the SWG was blocking in the previous example, right? And it's the same malicious file for all of these channels that SWGs are incapable of monitoring. Interestingly, some of which they acknowledge, others they don't even acknowledge in any of their public documentation. So literally, the attack is as simple as you click, it downloads. So the most important thing I want to show over here is the user experience of clicking on something and downloading is not changing in any way. So the whole attack over here is something which is absolutely seamless and transparent to the user. The only thing which is happening is, rather than using typical HTTP-based communication, we are using WebRTC, gRPC, and a bunch of other options. As I said, when we actually set this one up, it didn't even feel like we were doing anything interesting. I mean, the most fun attacks is when you go and barge in through the main door and you still get through, right? Well, we have a bunch of them, so. Okay. So in the interest of time, I'm just going to move on to the next attack. So this is the website which you guys can access right after browser.security. Okay. The next one is what we call hiding in plain sight. And this is really about now sending data through a SWG, but trying to look at things which SWGs can't analyze today. How many of you have heard of WebAssembly? Okay, some folks. So WebAssembly in recent years has gained a lot of popularity. Allows you to go ahead, compile a lot of native libraries and run it within the browser itself. And WASM files pretty much just load in the context of a page. You have a JavaScript bridge with which you can talk to them and do various things. Where you find this to be used quite a bit is sites where image processing and all of that stuff is happening on the client side. So let's take a look at what we can do with WebAssembly. Now, the way the attack actually works is we go ahead, package the entire malware inside a WASM file. So we can convert the the malware as a payload inside WASM. And WASM is a binary format. Today, no SWG is capable of monitoring and analyzing WASM files. So the way the attack works is the page opens, HTML, CSS, WASM loads, and then we trigger a payload dumper from WASM, which basically then dumps the entire file, triggers a download event in the browser, and it just drops. So the end user experience is once again identical to you clicking a link and a file downloading. And as you can see, we triggered a download. This is the same malicious file. And by the way, the SWG which we have enabled is one of the top 3 in the vendor quadrant. No names. Now, then we said, hey, why not make this a little interesting? I mean, all of us love steganography. Almost impossible for a cloud proxy to analyze images for steganography. Millions of images get loaded. To create a custom steganography scheme is super trivial. I think almost everybody goes through that rite of passage when you just start building backdoors and whatnot. So here's what we did. Let's move on to the, just show up in a bit. Okay. So the image you see there with the parachute, which says AV, antivirus or next gen, that image actually contains the entire malware in it, standard steganography. So now what happens is the attacker loads a web page. Let's say the victim clicks, via social media. And on the page, there are images which contain the malware payload. Via JavaScript, we actually pick the payload from the images, construct it together, entirely on the client side, then drop it onto the user system. I'm recovering from a very bad flu, so apologies if I have to cough in between. All of this code will be available. Browser.security is completely open source for you guys to try. Again, evades every single SWG. Okay. I'll have Shaurya talk through the next few. It's going to give my throat a little bit of break as well.
Thank you, Vivek. So now we'll look at some other mediums through which we can actually do the same thing. We can also use the standard HTML components. Like it could be, a simple JS file, or it can be a CSS file, and even an SVG file. So we can actually embed the same malicious file, for example, as a variable in a CSS file. And what the client-side code will do is that it will simply read the style sheet, pick that particular payload from there, from the CSS variable, and drop again as a download. So, these kind of attacks are slightly, I would say, embedding based, because you're embedding the whole malicious file as a byte array in a particular variable inside a JS file or a CSS file, or in fact, a SVG file. So, quickly seeing the demo for this. Yeah. Yes. So the next one we'll see is actually an HTML embed. So in HTML embed, we have an HTML element, and that element has the whole malicious file embedded inside. And using the JS, we're going to read the contents of that element and then construct a file and trigger a download. So whenever we are doing these client-side download triggers, these are basically blob-based downloads. So if we see here, we can see the attack went successful just by having the whole malicious file embedded inside that HTML in an element. The same can be done for other resources as well. We're going to simply, just put the whole malicious file as a byte array. So in this one, we're going to try with JS. So we have like a huge byte array inside a JS file. And then again, doing the same thing, picking it up from there and then triggering a download. So all of these were actually bypassing. Similar to this, we can do the same thing with the CSS file, and can also be done for an SVG file. Now going back, this is how it works like. You basically open a page. In that page, you have these files which have the embedded malicious file. And on the client side, you trigger the download. Now let's look at some other ways we can do this. And this one is the interesting one because this is the last mile reassembly attack. Now, in this, what we're going to do is that, like Vivek mentioned earlier, all the secure web gateways are looking at the traffic at a network level. So they don't have context about, all these network requests are actually coming for a single tab. And with browser, information about a single tab becomes quite important. So what we're going to do is we're going to simply break the file into different chunks. Now, this breaking can be done in different ways. So first is a straight chunk, so a straight split. So in this, we're going to simply split the file into different chunks, trigger the download. So to trigger the download, first we have to fetch all those chunks. So at the client side, we will make multiple network requests to fetch these chunks. Once we have all these chunks together, we're going to use the JavaScript to put them all together and then trigger a download. Now, SWGs, they will basically look at these requests individually. And looking at an individual part of the file, they will not be able to understand if it's malicious. Now, we can make this even more complicated by doing something called as a reverse split. So in reverse split, we'll basically take a chunk and reverse the content of it. This will make it further complicated for them to analyze individual chunks. Again, it can be made further more complicated by changing the size. So let's say I make different size of chunks and try it out. That will also bypass it. The last one is mixing and matching all these things together. So we can have a case where we have multiple chunks. Each chunk has a different size. Some of those chunks are reversed, and some of them are not reversed. So on the client side, the attacker will know what is the correct order and which particular chunk has to be reversed and which doesn't have to be reversed. So again, the process is same, that we're going to send all these files across in different network requests, all these individual chunks. And on the client side, we're going to use JavaScript to put them all together and trigger a download. So we'll just quickly see the demo for the same. To be able to see all these requests coming in, we also have the network tab open here. So we can see here, the attack went through because a single file was broken up into different chunks. And they were able to see only individual requests at the SWG level. Dragging the same file will show that it's a known malicious file, which ideally should have been blocked. The same can be done for the other varieties as well, where we're going to split it into different chunks, but reversing the content of it. And then the same could also be done with the randomized size and also with a mix and match. After this, we have evading this using encryption and decryption. I'll ask Vivek to come back.
So I think you guys get the drift. The whole idea about last mile reassembly is you have the browser as a final machine where you can run code. Rather than giving the SWG, the entire file to analyze, to basically reassemble and build things right in the browser itself. And literally, you can take this to any level that you want. Imagine that if you wanted to build a malicious document, you could literally have a WASM module which is creating an Excel sheet right there on the client side. The Excel specification is open. There are a bunch of libraries available in different languages, which you can compile into WebAssembly. Very easy to do, by the way. And then you construct the entire Excel locally. So now what happens is, from a SWG's perspective, a file was never downloaded because there is never a content disposition header triggered. There was never anything which is happening, anything closely related to a file. And this is very potent because from the SWG's perspective, it's just loading pages, nothing more. Now, you can keep building on this. So when you look at encryption, decryption, most of the times we might imagine that an attacker is, let's say, encrypting a piece of malware in a zip file, sending it to you with a password, and using some kind of social engineering to have you open it. But thinking of it from a last mile reassembly, imagine that even if you send the same file but encrypted, but on the browser, you can decrypt it in memory and then drop the unencrypted file, right? So again, from the user experience perspective, he clicked on a file, download on some website, and it just downloaded. But what is really happening is you are using the browser finally to do the heavy duty part of unwrapping all of those onion peels and then dropping it. I mean, you can pretty much use any encryption schema. And so we put out 25 different bypasses, which currently pretty much works across all the top SASE, SSE, SWG players. I'll have some vendor responses at the very end as well. I mean, if you're wondering if we approached vendors. So all of this is completely in browser, totally transparent to the end user. And I know most of it just looks like click and download. Sadly, that's how easy it is to orchestrate the attack. And that is what makes this so potent, because there is no change in user behavior. There is no change in the way that the user would have to interact with the attacker's website. It is pretty much all the same. Okay. Now, similarly, I mean, you guys get the drift, is you can do encoding and decoding as well, right? So you can apply any form of encoding schema and decode it entirely on the client side. I mean, UU encode, base64, whatever you love. SWGs at this point in time absolutely have no clue about how to look and interpret that data. So you can send a binary stream and just works. Okay. Now, what is worrisome is all of these attacks, at least to the best of my understanding, I mean, I'm not a lawyer, but breaks the SLA, which basically says we will not allow any known malicious malware sample to be able to leak through our secure web gateways, right? I mean, I don't know, unless there is a legal addendum where the definition of that is something different. Okay. So moving on, we said, what about file uploads? And this is interesting because a lot of organizations worry about insider attacks, right? What happens if someone just ends up uploading hundreds of documents somewhere? How do you even know? At this point, the SWG promises that it can actually show you who is uploading what documents. You can get all of that audit trail if you wanted. But now, just apply last mile reassembly, but in the reverse direction. So imagine that I'm an insider, and I'm an inside attacker, and I have set up a website, and here is what I do, is when I want to upload a file, on the client side itself, I actually apply the same transformations which we did in the reverse direction, and send the file data out. But now it's not a file at all. It just looks like a form submission or session data or something else which is being sent. I'm not even talking about the unmonitored channels like WebRTC, gRPC, and all of those channels, right? This is absolute plain sight, but going and uploading, but not as a file. So WebDLP will not trigger at all if it does not detect something to be a file upload. There's absolutely no way for it to apply any form of regular expression, binary matching, or any of that, right? With this, we've actually found 100% bypass of pretty much any DLP rule. Because again, just commonsensically, you're not sending a file. The attacker is able to break that down on the client side and just send it as data rather than file. So let's show you how that looks like. Okay, so we showed that we basically have a file upload of a malicious file. And now, let's take a look at this one. As expected, a SWG ends up blocking it. So now let's actually go to the list of attacks we've created for file uploads. Now, some of these we even played along and said, okay, we know how to send this as data. Why not send these as chunks? And let's see what happens, right? Some of you folks who may remember how the old network attacks used to happen, IP fragment reassembly attacks, anyone? Where literally you could go ahead and play with the fact that your end system looks at IP fragments in a different way, and the way it would end up reassembling, especially when it comes to things like overlapping fragments, is very different from how a network device would look at it. Because a network device doesn't really understand how the IP fragmentation stack is looking like during all of this. So we said, hey, why don't we try to play with all of this? Because if you think about it, if I'm an insider and I set up a website through which I want to exfiltrate documents, I could actually bring back all of those older attacks of overlapping fragments and all of that and actually apply it to all of this. And as expected, there is full bypass. We have malicious websites after that, and trust me, that's going to blow your mind. Okay. Okay, we have 5.5 minutes. I'm going to breeze through a little bit. Okay, phishing. This is the talk of the town when any SWG player comes in. Everybody tries to sell you phishing detection. And we said, let's take a look at this and see if attackers can completely smuggle through malicious websites. So let's look at a SWG in action first. When it comes to malicious website detection, So here is an example where what we've done is we've picked up 3 URLs, all of which contain phishing websites which SWGs detect. Now, of course, without a SWG, it opens up. Now, let's see what happens when a SWG is enabled. As expected, access is restricted, right? So we said, hey, how do we solve this? Because if you took the same phishing website, even change the URL, some of the better SWGs will still detect it. Because the files are the same. I mean, you probably can change some fingerprint, but nothing beyond that. So we said, let's try a few fun things, right? How many of you try to save a web page as web page complete, and it ends up saving it in an archival format called MHTML? Anyone done it? Almost everybody, I'm guessing, right? So we said, let's take the same phishing website, convert it into an MHTML archive, and now let's actually load the attacker web page. This MHTML archive, of course, SWGs don't even look at it, but even if they did, we can use the file download reassembly attacks to anyway smuggle it on the client side. And then, using JavaScript, we take this, use the canvas, and completely repaint the UI, where now the phishing website reveals itself entirely on the client side. So the best example is, imagine you send a painting which is banned, through security, and they look at the painting and they're like, you know what, this isn't allowed. And that's your phishing website, right? Because we've seen it. But now instead of sending the painting, you send a painter. And once the painter arrives, at your premises, he draws out the entire painting which was banned. So last mile reassembly for websites is really you constructing the entire phishing website entirely on the client side. So let's show you how that looks like. I mean, there's a bunch of stuff. Unfortunately, it is a short talk, or else we'd love to go with this for hours. But you'll see how powerful this is when we apply this to SWGs. OK, so here is the attack. And now what is happening is, the page, when it ends up opening, the same malicious AT&T website which you'd seen, that's actually getting sent as MHTML using the file download reassembly attack, completely bypassing the SWG. And all the website JavaScript does is picks that up, uses canvas rendering, completely repaints. For the end user, there's zero difference. He basically just ends up seeing the same malicious website, right? But from a SWG's perspective, it is completely blind because it absolutely does not know what finally gets rendered onto the user system. So you can now literally reuse older phishing websites with ease, because now there is no server-side detection happening. The whole thing gets created on the client side. And by the way, this is literally we doing websites on every single threat feed out there, probably for a few years. OK, almost running out of time, so I'm going to be fast. You guys have seen this. Now, why are these architectural issues? Well, the big reason is all of this is completely happening on the client side on the browser. SWGs run on the server side. So for them to really understand what is happening, the only way is when any HTML, CSS, JavaScript goes through, they literally have to create an emulator on a per client basis. Now, this isn't even possible because SWGs don't have notions of tabs and windows, right? They're just looking at flat traffic. So when they look at two requests, they can't make out if this is coming from the same tab or window. For them, each of these are independent. So which means you do not even have enough data available to do any form of dynamic analysis in the cloud trying to emulate what is happening on the user's browser, even if you had access to everything. The other way is you do literally a live sync when things load in the browser back to the cloud to inform, but that is impossible to scale. Like imagine 20, 25 browser tabs, hundreds of browser events in a second. You don't even know which ones are changing what. just not possible. So what really happened is there was a time when I guess people figured the best place to build a security product is where you have the richest data. And then came cloud security SaaS, where everyone said, look, if we just do this in the cloud, it's going to be easy. It's also going to be lucrative. Now, this is really where what our contention is if you had to build a client-side web attack product, it has to have a browser component. Because without having access to DOM events and a bunch of other things, it is just impossible. OK, I'm going to just go through real quick. SLAs break. Last slide, vendor responses. Vendor class A agreed, said they're probably going to work on a solution or are working on a solution. Vendor B told me they detect some of this, which was very surprising. So I said if they were willing to make a public statement, I could actually show on the slide at DEF CON. All of a sudden, they went cold. Vendor class 3 was the most amusing. I did not know if they actually dropped off the Zoom call, because I heard nothing till the very end was just a thank you. OK, so after this, in a couple of hours, browser.security, all the source code will be open source as well. You can go try with your SWG. And hopefully, vendors who are watching, don't shoot the messenger. Do not block browser.security and claim that you've solved last mile reassembly attacks. All right, thank you so much. Thank you.